okay?
So can A and B independent events? I'm pretty sure the answer is yes. If so, because there wouldn't be a subsequent question. Show in a diagram the probabilities of the intersection of A and B and the probability of the complement of the union of A and B. So to me, this is a Venn diagram. I'll show you my art skills.
Yeah,
So
definitely. This is
definitely the union, right?
Yep.
Sorry, no, complementary. Which one is it? This is the
Complement.
one. This is the complement.
It's
right?
an intersection. I'm sorry. That is the probability of A intersection B.
Exactly, right? Which is one of the questions,
Yeah,
right?
yeah.
It's the first one. And so I was able to show that. But then it asks for the complement of the intersection. No, sorry, the complement of the union,
Yep.
right? And I think that's this out space, right?
Yeah, it's true.
Okay. All right, cool. That was that was what I was unsure about. It's basically everything else, right? The whole Venn diagram is what it's asking.
Yeah.
And the complement is the box, right?
True. So what you need to know is inside that huge rectangular, it's a probability of 1. That's
Yes.
100%.
Yes.
And that two circle you need to calculate by yourself. I guess it's like 0.4 and 0.7 something, right?
Oh, so these need numbers. I can't just put the probability. They actually need numbers.
It's better if you have the numbers. Because the assumption is that's independent event, so that gives you some ways to
enough
calculate the
information.
method. Yeah.
Okay.
Victor, is it 0.7 times 0.4 minus 1?
I mean the 0.7 times 0.4 gives you the intersection, right?
Yes.
Because that's independent event, and then you have to find what is A union B, and 1 minus union B. A union B gives you the A union B complement. So you need to find what is the area of that two circles, and
1 minus union B.
Yeah. So when you're trying to calculate the complement, you have to first calculate the union, right? And then you use 1 minus A union B, and you get the A union B complement. So you should first find what is A union B. And there is a formula actually. So in every cases, no matter independence or not, A union B equals the probability of A plus the probability of B and minus the intersection, right? If you can look through the Venn diagram. Because when you use probability of A plus the probability of B, you are double counting the intersection part. So you need to minus that from the formula.
So the A and then the upside down U is union, and the A with positive U is intersection?
No,
Upside
U
down
is union.
Yeah.
U union, upside down is what? It's intersection.
Yeah, U is union.
U is union, which is wonderful, right?
Yeah, U is union, but then, okay, and then A upside down is
intersection. Oh, sorry, union also ends in an N. Yeah.
Okay.
I don't know where you're going to.
Well, look, that's an N, right? Like that upside down is like an N, right? Intersection.
Okay.
We have a bunch of people here.
And it's just saying true.
Hi, nice to see you.
You got a haircut.
You can see the screen. I just write this is a very general, sorry, it's a generic formula. The probability of A union B, it's pretty ugly handwriting. I don't get a mouse. So it's always equals to the probability of A plus the probability of B.
But so if A union B is A plus B, then is there a min and a max value, or is the min and the max the same?
The min and the max. There is a min and the max.
So if A union B is A plus B minus A intersection. How is there a minimum and a maximum? Like, where does the min max come
The
in
min,
place?
wait, hold on, I was just.
So
Min
what
opens
part are you
the
talking
small.
about? It's like part C,
Just
right?
the concept of like a minimum value versus a maximum
So
value.
for example here, if you want A union B maximized, then you're going to have A intersection B minimized because you just look at this formula, right?
So it would, like, one way to interpret this is, imagine if you move the circles on top of each other.
Yeah,
Okay.
that's true. That's true. So that's the geographical way is to think like you are moving, like they are
Yep.
touching each other, or sometimes the B is absolutely inside the A. But if you just look at this formula, you'll find that the probability of A is zeroed, which is 0.7. The probability of B is also zeroed, which is 0.4. So there's two things that are changing, which is A union B and A intersection B. So whenever I find the minimum value of A intersection B, that also means I find the maximum value of A union B, because the dynamic thing is only these two. So whenever one goes maximized, another automatically goes minimized.
Okay. Cool. I think I can finish this one.
Okay. I have a question on
Those
two.
aren't bad, yeah.
Um,
I didn't even
Oh,
get
I'll
to
turn the
this.
screen.
Okay.
Hey, Thomas. Wait, Thomas, by the way, you're here with Paloma and Olivia. It's a whole
Okay,
crew.
sure.
Guys,
This
we're
is Bobst, right? You're not like using like a study room something.
This is Bopes, yeah.
Oh, sure, sure.
We got kicked out of the KMC last time for staying too late because it closes at 10.
Okay.
Why are you less envious that we're in Bopes? We're in a graduate room, special room.
We'll give you special access.
Okay.
So the probability, this is 2A. I don't know why it's 2-1, but I'm going to call it 2A. So I feel like that was pretty straightforward. It's applying the exact same concept of intersection and union and basically saying and or, like what's the probability that a player selects two numbers independently, right? And one or the other exceeds some value. So like that, I think that's straightforward, and we're applying the same concepts.
Yeah, so it's like at least once I have to exceed a certain value.
Right. So it's or, right? So it's either or needs to
Yeah.
either selection, right?
So actually there's like three choices. First, I exceed the certain value during my first try. The second option is I failed during my first try, but I succeed during my second try. And actually there's option 3, which is I succeed in both tries. So actually you're right. So it's like a union. Yeah.
Right. And so I need to know that if the probability of the first try is 1, or sorry, the probability of getting a number higher than 0.5 is
Yep.
0.5.
Yep.
And the probability of picking a number the second time higher than 0.5 is 0.5. So the probability of A is 0.5 and the probability of B is 0.5. And I need to know the probability of A or B.
Yep.
But yeah, that's straightforward. So then we need to work backwards and say, well, what is the optimal value of, I guess, beta? What's that Greek symbol?
Yeah, it's beta.
Beta. So what is the value of beta which would make the game fair? And the way that I wanted to put this equation together is that we can assume the probability of each selection is the same, right? So like no matter what the number is, the likelihood that you select it is always going to be the same because it's the same number of times, right? So that means your formula for the additive rule of probability. So the formula where it says the union of A and B is equal to A plus probability of A plus probability of B minus the intersection of A and B.
Yep.
Can be simplified to the union of the events equal to effectively 2 times the probability of that initial event minus that same probability squared.
I think it's true. Yeah.
Right. And so I would assume that we want the outcome to be equal to 0.5. So here's my formula, and I'm having trouble simplifying it. So I'm saying 0.5 is equal to 2x minus x squared, right? Which is the simplified version of that equation, right?
You're doing part B, part A or part B?
Part B.
Okay. Yeah, you're doing part B. True.
Right. So am I on the right path?
You're writing. I believe you're writing a right formula. So just but you have to solve it. Yes.
Yeah, but solving it leads to radicals, which I don't like. Like it's not a straightforward, not radical, square roots.
Yeah, it has square roots, definitely.
Okay.
But
All right.
But like maybe you can convert that to like 3 decimal places, something. Yeah.
Okay. All right. That's all. That's the guidance I was looking for.
Yeah.
Okay. Thank you. Just making sure that I'm not like going crazy. All right.
Yeah, that's a correct method.
Okay. Thank you. Go ahead.
I'm stuck on 2A.
Yeah.
So if you pick two numbers,
Yep.
like you said, A can exceed 0.5, B can exceed 0.5, or A and B can exceed 0.5.
Yeah.
So what's the probability of the player winning if the number is, if the like minimum is 0.5 that they need to achieve? How, I don't even know how you go about that.
Okay, so I would say maybe I use the capital letter A and B to represent the two events, right? So the capital letter A represents I win the game from my first try.
Yep.
This is capital A. And capital B represents I win the game through the second try.
Okay.
So basically this problem asks me to calculate the probability of A union B, because I can win this game through the first try or through second try, or I pick two numbers and both of them are exceeding 5. Yeah.
Oh,
So
so you either get it here or here or here?
yep.
Wow.
So that is A union B, and you can just use the formula I just write down on that homework page. So A union B equals A plus B minus A intersect B. And what is the probability of A? It's simply 0.5, because it's just a single event. I just choose a number from 0 to 1, and it exceeds 0.5. So the probability is just 50%.
Because if you pick anything between 0 and 0.5,
You lose.
which is 50%,
Right.
then you lose.
Yeah.
So the probability is 50%. And then on the second try,
Still.
50%.
Yep.
Oh,
So the tricky thing is A intersect B, but I guess you already how to calculate that from the first problem, from homework 1, from problem 1, because those two are independent events, right? It doesn't influence the probability of winning from my second try. So actually, like, to put it on this way, the result of my first try have no impact on the result of the second try. So
Agreed.
that means these two events are
Are
independent. Yeah.
and the probability doesn't change.
So the probability of A intersection B just equals to their own probability multiplied. So it's 0.5 multiplied by
Got it.
5.
Okay.
Yeah.
Okay. And then when I make a game fair, that just means 50-50 shot.
So you first you find your answer in first question. I think it's definitely higher than 50%. So in
Mhm.
part B, you have to create your own beta to make the answer exactly equals to 50%. So basically, you will set up an equation, and you're gonna solve the equation to get the beta for a 50% chance.
Okay.
Yeah.
Mm. All right. And then the next set is talking about the time until failure of a certain piece of equipment.
Yep.
So we're saying that the user pays for the equipment. They don't pay anything if it breaks in the first month.
Yep.
First month.
We need an exponential formula, right?
Yeah, you're gonna use that formula. This is very important. I mean, this formula is very important. You have to understand thoroughly what does this mean.
But isn't there using the exponential distribution and its then application, right?
Yeah.
So
Can you refer us to somewhere in the text?
I mean, for example, just plug in arbitrary number. So that's, I mean, a very important number is 0. When t equals 0, what is this probability?
So
It's just e to the 0 power, right?
right.
So it's 1. So what does this mean? It means like all the equipment from the beginning, they are functioning. At time 0, they are all functioning. And
one means functioning.
Hold on. How do we? Shit. How are we supposed to use that approximation though? I think that to me is a little bit confusing. We're
it's
e to the
just
negative.
so it means the e to the so this is just so if I put a t uh, after it, like e to the minus 0.69t is here, this formula. If I just put t outside here, it's just equals to 0.5 to the power of t.
Oh, 0.5 to the power of t.
Yeah, yeah,
Oh, I think that's where I messed up. Okay.
yeah.
0.5 to the power of t. Oh, okay. Okay. So the probability of zero payment is the probability that t is less than 1.
It would be
Yeah.
0.5 raised to the 1,
Yes.
which is there's a 50% probability that they don't pay anything.
Yes. So 0.5 to 1 month is 50% probability. And then probably that the payment will be between 10,000 and 30,000 would mean that
That's at the end of month 1. So T equals 1.
it's between 1 and 4.
And so then the second month is 20,000, then 30,000. So this is month 1, 2, 3. It's month 3. It's T equals 1 and T equals 3.
Yeah. So
Hold
if
on.
I'm writing that in that formula, it's like
don't-
probability
That's
from
not.
1 to 4, right?
No, it's not. It's 4. It's not 3. So it's that occurs in the third month.
Yep.
T equals 0 is the first month.
And so
T equals,
$30,000 is a failure occurs in the 4th month.
which is T equals 1, 2, 3,
4.
but the second month is T equals 1.
It's pretty tricky. You have to understand what is the limit.
0 to 1 is $0. 1 to 2 is 10,000. 2 to 3 is 20,000. And somewhere at 3.2, 3.3, 3.4, 3.5, 3.9, sorry, in the third month is 30,000. So you have to go up to 4.
Oh, got it. Okay. Okay, got it.
But that means we need to know the probability of 10, I guess the min and the max. So we need to know the probability that the payment will be 10,000, and the probability that the payment will be 30,000.
But it doesn't say, it doesn't matter what day it is. As long as it's in the second month, we pay 10,000. That's the way I read it.
Which is correct.
Not, so it could be 2.1, 2.5.
Exactly.
Okay.
Exactly.
Yeah.
So the probability the payment will be 10,000 is 0.5 squared, right? And the probability that the payment will be 30,000 is 0.5 to the fourth. And so you would want to know I think it's the cumulative probability. So I think it's it's the cumulative probability of 10, 20, and 30. Oh, sorry, of 2, 3, and 4. I think you add up 0.2, 0.5 squared plus 0.5 cubed plus 0.5 to the fourth. What do you think, Victor?
It could be the case. So basically, you are calculating the probability of the equipment failure during the first month plus the probability of equipment failure during second month plus the equipment failure, the probability of the equipment failure during the third month. So basically, what you are doing is you take 3 probabilities and sum them up, right?
Yeah.
This is a correct way, absolutely. But first you have to understand this formula here. You have to understand this formula here, in order to calculate what is the probability of failing in every month. What does this actually mean? So for example, if I just said t equals 2, what does that mean? When t equals 2, the e to the right hand side, this part just equals to 0.5 to the power of 2, right?
Mm-hmm.
What does this mean? 0.5 to the power of 2. What does this number mean?
It's the probability in the second month that you will fail.
Not necessarily. You have to understand this formula.
So
why it says from t to
So-
unlimited to positive infinite? What does that mean?
It's the probability that you will not fail before that time.
Yeah, it's correct. It's correct.
So it's basically saying, what is the probability that I won't fail between the beginning and the time of interest? Rather than saying, like, I am going to fail in some time period. It's like what's the probability of some period of time will pass that I won't fail?
So how would you explain that for the first statement? If t equals 1, what does that say? Saying the probability that t equals 1 to infinity?
Yeah, so find the probability of the zero payment is saying what is the likelihood that I don't fail in the first month, right? Not the likelihood that I fail in month 2, because you could fail in. That's not the way the formula is designed. It's likely that I don't fail in the first month.
Oh, so it's like a 0-1 game.
It's more that your known element is like between now and some time of interest, and that because it's infinite, you can't know when something will happen. You just know what won't happen.
You don't know when it will fail. You just know it won't fail in this month.
Yes.
Oh.
So you're not predicting success, you're predicting the lack of failure.
Wow.
Is that right, Victor?
Yeah, it's good analysis. And another way, like when you saw this thing,
I gotta say, you're so evasive when I ask you for validation. I feel like you don't want to like confirm what I have to say.
I think what you said are right.
He's an actuary.
I know it deals in absolutes. That's all right.
Yeah, yeah. One word to make my opinion is correct. But again, I mean, when you saw this kind of formula, what I will do is I will take some arbitrary number into it, because I think that will help me to analyze this question. For example, when t equals 10, what does that mean? When t equals 10, you'll find the right hand side is extremely small.
Yes. So the likelihood that
it's like 0.5 to 10th power. But what does that mean? That means the probability of this equipment fails after month 10 is pretty low. It's very low. So it means the probability will probably fail before the 10th month.
exactly.
So that's how you analyze this problem. Yeah.
So we're talking in this sort of scenario, we're talking about like if you buy something and it's defective, if it doesn't indicate to you that it's defective in 4 months, it's not a defective product.
Yeah, because it will
not. It's like
Yes.
It's not like a light bulb where after a certain period of time it will die. You're talking about like if you bought a lemon car and the car broke down after 4 months, then it's a lemon and it broke down. But it's saying if it hasn't broken down in 10 months, it's not a lemon.
Basically.
Okay.
Right? Like if you pass some threshold, right? Let's say the 10 months puts you at 0.01% chance that it will break down after 10 months, then you've made a good purchase. And the likelihood of it breaking down at this point is extremely low because you've passed the window of high likelihood.
It's not how I think about equipment. I normally thought it would be the opposite.
It's like time to failure, which is, yeah.
How many bonus points do we get if we get 3? The bonus very challenging.
25, and you can show your work.
I'm writing.
25 points, and you can show your work to get partial credits for burners.
Oh wow. Okay.
I need 25 points.
That is generous. That is extremely generous. All right, but I feel like you have no appetite to help us on that problem. So, understandably, because it's bonus. Okay.
I would say like every time you see the expected payment, the expected value, you use the probability times the value. That is the hint for number 3. I mean, the setup is not too difficult for part 3. So the formula is not too difficult, but the calculation is very difficult. It's an infinite series, and it's not a simple geometric series. So you need to play with some algebra in order to calculate the final expected payment. But the setup is not difficult. You just so you find you will use the same method for the part 1 and part 2 because the payment for each month is different. So absolutely you need to calculate the probability of the failure in each month, and you multiply by that probability by the compensation. That will give you the expected payment. The setup is not too difficult, and you could try how to
This is
calculate.
it was basically taking the integral, right?
This is not taking an integral. So taking an integral is for like continuous distribution, but here it's not continuous. Like,
that's true.
Yeah.
Because on the first day of first month and the last day of first month, you all get paid for 10,000. So it's not continuous. We would say it's discrete. For any discrete, expected value. It's just the expected value is equals to like the value times the sum, actually the sum of let's notate a sum of each value
Right.
times its probability.
Right.
Yeah. But this is an infinite series though. But because it converges, so definitely, so like, in the end, you find it converges to a certain number n. But you're not using integral because this is a discrete thing.
That makes sense. That makes sense.
Yeah.
If it fails in the second month, it's 10,000. If it fails in the third month, it's 20,000. It's not 10 plus 20. It's not like something can fail in the first month and the second month, right?
Yeah, absolutely.
It can fail in 2
No.
months, or it can only fail once.
I mean, what you said is correct. So
Right.
first month compensation is 10,000. Second month compensation is 20,000, and all the way goes
So it's
on.
not cumulative. It's just
Right, but you could say the likelihood of the first month failure is 50%,
Yep.
and so
So
you're
basically, you're using
valuing
50% multiplied by this 10,000, and you get the first expected value
Hold on. No, 50% times zero.
times 0. Yeah, you are right. You're right. And
50%
then,
times zero. Don't try to trick me, Victor. Come on. So it's 50% times zero plus the 0.5 cubed times 10,000 plus 0.5 to the fourth times 20,000. But I could do that from now until tomorrow at 6 and still not get to infinity. So I have to come up with a formula that properly.
yeah, but isn't the 0.5 to the whatever is going to get really small by the time you get to a certain not super high number.
So exactly, I only would have to write it out 10 times manually, and Victor would probably only give me partial credit for not coming up with the actual formula, right? So I do get to an approximation, right? And it does get quite close, so I might get partial credit, but I wouldn't get full credit because I haven't set up a formula that represents the infinite sum.
Wow.
Isn't that right?
if you remember, like there's a formula for like an infinite geometric series. Like you can now Google it, but here it's not a geometric series because every time here the value is different. You are multiplied by a different value. If this value is, for example, stays the same, then it's just a sum of a geometric series, and it's not that challenging. So
not Googleable, then it's not possible. That's what you're saying.
I think so.
Are you saying we can Google this?
Definitely, but it depends on how you Google it.
Yeah.
If
Okay.
you don't know the right method, you don't put on the right keyword, maybe you cannot get a right answer.
Right. No.
Victor, please Google.
I understand the nature of that exercise. But thank you.
Okay.
Thomas, we've been hogging the airtime. Is there something that you wanted to ask?
No, I guess you guys have pretty much run through what I was going to ask. Also, just going back to 3B, I guess. So when we say t equals 4, we're saying that's the probability that it fails between t and infinity, correct? Not 0 and 4?
Yes.
So if we're looking for 0 to 4, then we need to do 1 minus that formula, 0.5 to the 4, right?
Yes.
Okay. And so for a payment to be between 10,000 and 30,000, it will either be, it's between 1 and 4. So we're doing the difference, right? We should look at, let's see, so it'd be 1 minus the probability of t equals 4, then again, subtract out the probability of t equal to 1.
Yeah, exactly.
That's how I had it set up, right? Okay. Okay.
So basically, you just have to plug in t equals 1 and t equals 4 in that formula, and you do some subtraction and complement. That is basically how it works.
But so
Okay.
hold on. It sounds like we just walked down two different paths of the same answer.
Yeah, definitely. So you are like calculating the probability of each month and sum them up. And Thomas was like, he is utilizing this formula and just plug in t to get a right answer. Yeah, yeah. Basically, it's two different methods, and either method works.
Okay, I'll look for bonus points by doing both methods.
Yeah, definitely.
Another 25.
25.
Okay, cool.
Victor, I have a very important question for you. Our professor gave us a lot of examples. I don't know if you saw this. He gave us like 16 examples in class. What are the office hours to go through the rest of these?
When I graduate.
Exactly. I mean, he gave you examples, but like didn't give you the solutions or something.
That is correct. Do you have the solutions?
No, I don't have like I just sent an email to Professor Bartman. I expressed that you guys need more examples. That's something I talked to him, and he said yes, I will give them more examples during the class. But I think it's during the class. I mean,
Yeah, but we don't have the answers.
I thought he's
No,
like
no.
going over all the examples during the lecture, but
We skipped around a bit. We did, like,
some of them.
5, and there's 16.
I mean it's better. 5 is better than 0. I mean, but
Yes, I agree. Good work, team. But you don't have the answers to the rest of these though,
I
right?
don't have any. I don't even have your like examples. Like for this week, I don't even have class slides, but I'm okay. I can handle with that. So it's not that complicated so far. So
Okay.
so I can still handle it. But I'm sorry, I don't have any examples or solutions.
That's okay.
But if you have some particular like questions regarding to those, you can just send me an email and like take a picture of the examples and what you have done, and maybe I can talk to you later. And I mean, first I need to work on it by myself. Yeah.
And I can also send him an email to see if he can send the answers.
Sure. I guess he has the answer. I guess
I'm sure he does.
he is not making up those problems by himself. He's just like Google something. I mean.
Are you sure? Because the grammar and spelling of the questions would suggest that he types.
Okay. Maybe that will be the case. Yeah, I hear you. I totally understand what you're talking about. Right?
The comment piece.
It's a grammar of a statistician. It's not the same as everything else. I mean, yeah, true.
As we've come to learn. Okay. You guys have any other questions?
No, Victor got us prepared.
Thank you, Victor, for the time.
Sure. And now I will record this and put the recordings on the YouTube channel pretty soon.
Thank you.
Okay.
I watched them before.
Thank you. Appreciate it.
You're funny.
Sure.
Thank you.
Thanks, Victor.
Sure.
Bye.
Bye. Have a good night.